Let's try another example. It's on page 331 in the textbook. It's example 10.2. We're going to use equation 1011 to calculate the period of a spring's motion. So we have a 345-degree mass that's connected to a spring with a K, or a spring constant of 35 newtons per meter. And we're trying to figure out what the period of the spring's motion will be. So here's equation 1011. Equation 1011. And that looks like this. We've got our t is our period, is equal to 2 pi times the square root of mass divided by proportionality constant, or our spring constant in this case. So the first step in using this equation is we need to convert our units, because as you'll see, we have this mass that's in grams. So let's convert that. So 345 grams, so mass, will end up equaling 0.345 kilograms. Okay, and then we have another numerical value here, which is our spring constant. We'll be able to plug it in to that. So we're trying to find out the period. So this is what it looks like. We've got our period is equal to our 2 pi, and that's always just going to be part of the equation, times our square root. And we're just going to deal with the stuff inside the square root now. So our mass is 0.345 kilograms meters, and that is on top. And then we have 35 newtons for our K. You can just go ahead and delete this as I get a little bit better at using this here. Okay, so it's divided by 35 newtons meters. So I flipped the Newton meters, because when you divide by dividing by something, it ends up going into the numerator. So that's how it got up here. So if I was to just start getting things ready to cancel, 0.345 kilograms meters, and then 35. So a Newton would change over to being kilograms meters, and then per second squared. Again, dividing by a denominator ends up putting it on top. Okay, let me put the rest of my equation so everybody can follow it. So now we have some things that we can cancel. Let's see if I could do that in a different color. We're going to cancel our kilograms. We can cancel our meters, so then we just end up with seconds squared. And it's under this square root. So that's going to be pretty easy here to cancel things. So let's just carry everything down, times, we'll just split it up here, 0.345 divided by 35, there's my numerical values, times the square root of the second squared. That simplifies just out to seconds. And then we have our square root of 0.345 divided by 35, and we end up with the square root. This is what it'll look like in your calculator. 0.009857 and onward, times our seconds here. That, everything just follows and flows down. We haven't done anything with 2 pi yet, but if we take the square root of that, it ends up being 2 pi times 0.0993 seconds, and then we multiply all of these out, and I'm going to put the answer over here. Our period ends up being 0.62 seconds. And this is a 2 sig fig number here, because back here we're dividing by a 2 sig fig number. So that just makes our answer 2 sig figs there. To the next example, you can find this on page 332. It's a multi-step. So we're going to use all of the equations that we have covered so far in the textbook It's example 10.3. It's a multi-step. We're using Hooke's law and the period equation. So we have a spring with a 34.5 kilogram mass. Note they're saying mass and it's not a weight, right? So that means we're probably going to have to convert it into something usable. And it stretches a spring to 59.1 centimeters. Again, we're going to have to probably convert that because this is in centimeters and not meters. The student then pulls on it and stretches it an additional 35 centimeters. Now, let me say, this particular question is very, very similar to one you will see on the test. So what do we know? We know the mass, and we know that that's 34.5 kilograms. And we also know a delta x, right? Because the spring has stretched out after the mass was attached to it to 59.1. So our delta x is 59.1 centimeters. So we're not going to have to convert our mass. We are going to have to convert our centimeters. Okay, and then all of these equations so far, we've really had to use the gravitational constant. So that's negative 9.8 meters per second squared. We do care about the direction on this because we've got a couple of forces acting. We've got weight pulling downward, and then we've got our spring pulling upwards. So there are two different forces at play. So let's just go ahead and convert our units first. First step, we're going to convert units. We don't have to do anything with that one, but we do need to convert this 59.1 centimeters. So our delta x is 59.1 centimeters. We're going to convert that into meters so we can use it later. Cancel out nicely. So that ends up being 0.51 meters. I'm sorry, 591 meters. There we go. And this, since your displacement is a vector and we are concerned about directions here, this needs to be negative. Because why is it negative? Because we are going in the opposite direction of the force that the spring is exerting on the object. So if I've got my spring here, I've got my object there, my mass, of 34.5 kilograms. We're going to have a weight vector going one way, so our force with our weight, and then we're also going to have the spring pulling up because it wants to go back into equilibrium. So the upwards force that the spring is pulling on the weight, and that's keeping it at equilibrium, is our restoration force. Okay, so that here is the one that we're dealing with. And so we're making this one the positive, and this one's going to be in the negative direction. And again, we're not dealing with degrees, so you set the positives and the negatives. This is how I'm going, because negative is down, positive is up. This look a little bit more like a positive sign. Okay, so we converted a unit. Now we need to figure out what the K is, our spring constant, or our proportionality constant, in order to find our period. So step 2, we need to find K. So how would we do that? Well, this would be where our Hooke's law would come into play. I'm just going to label my force as my restoration force, and we can plug that in to Hooke's law. So Hooke's law is force of the restoration is equal to our negative proportionality constant, or our spring constant. In this case, since we're dealing with a spring, we're going to multiply that negative K times our change in our X, or our displacement. Okay, but do we know everything we need to know yet in order to be able to use this Hooke's law equation? Not quite yet. So let's try something else. So in order to find out what K is, we have to figure out what our force is, because all we have now is the displacement. So let's figure out what our weight force is, because once we figure that out, we'll be able to then find out our restoration force. So we're going to use our old weight equals mass times gravity. And I'm just going to say the force of the weight just so we know we're dealing with that right there. Okay, so our weight force is equal to our mass times gravity. We already know what the mass is. It's 34.5 kilograms times our 9.8, it's our negative 9.8 meters per second squared. And that's our weight. So weight equals mass times gravity. And what do we get when we multiply all of that out? Well, if I'm plugging values in, I end up with a negative 3.4 times 10 to the second newtons, because it's a force, right? So we need newtons. Or, you know, if you're plugging into your calculator, you might see something that looks like this, 338.1. But at this point, we're going to try to get to our significant figures. So you would end up rounding that to 340. Okay, so that's the same as that. You could write either of those and you will be just fine. I'm going to stick with the scientific notation for the next couple of steps. So let's move over here. Step 4. Now we have to find our restoration force from our weight force that we just used. Okay? Well, since we're at equilibrium, there's no acceleration. There's no acceleration or velocity. So we know that we're at the new equilibrium. So therefore, our restoration force is going to be equal and opposite of our weight force. Okay? Equal and opposite of our weight force. Okay? So our restoration force is going to be opposite to this. This is a negative, so this is going to be a positive. 3.4 times 10 to the second newtons. Okay? Because it's going back in the positive direction. Now we have enough information that we can use our Hooke's law equation. So we've got our restoration force is equal to our negative spring constant times our change in displacement. So we can take our values and plug them in. 3.4 times 10 to the second newtons is equal to, we still don't know the k yet, times, and our displacement is negative, right? Because we're going down. So that's what we have from up here. So we've got negative 0.591 meters. Okay? So here, a negative times a negative is a positive. So that takes care of that side of the equation. That's neat and tidy. Now we can isolate the k. 3.4 times 10 squared newtons divided by 0.591 meters. So here, I'll just highlight this in red. We've got our unit for our spring constant, or our proportionality constant, of Newton meters. So we're looking good so far. Now all I have to do is divide all this together. I'm going to see in the calculator that's probably going to look something like that, like a 575.3. And that's our value for k. But if I want to do my two significant figures, I'm going to have to round. So I could either round it to this, or I could do my scientific notation. We're getting familiar with the scientific notation, so that's probably the best one to use from here on out. So our k value is 5.8 times 10 to the second power Newton meters. And that's looking good. So let's go to the next step. So we're coming over here next after we've got our k value. And we're asked to find the period of the resulting motion. So we have one more equation that we need to use. And it looks like this. It's equation 10 11. So we've got our period is equal to 2 pi times the square root of mass divided by our spring constant. We have all the values we need to plug into this. So let's just do that over here. So our T is equal to our 2 pi. We're not going to do anything with the 2 pi until the end. But let's see what it looks like. We've got our mass of 34.5 kilograms divided by our 5.8, this is our K, times 10 to the second power newtons. And I'm going to put my meters up here because dividing by T equals 2 pi, we're still working under this here. We've got my 34.5, and then we're going to have kilograms. We're going to have meter divided by our 5.8 times 10 to the second. So newtons will break down into kilograms, meters per second squared. See, all of a sudden the seconds moves onto the top, right? Because so then we have, just like in the previous problem, we've got some cancellations to make. This simplifies things a lot. Canceling meters with meters, kilograms with kilograms. And that makes it so we just have our seconds squared here under our square root. So taking the square root of the seconds squared is just going to end up working out to be seconds. We're taking our square root of our 34.5 divided by our 5.8 times 10 to the second power. That just, you'll see on a calculator something that looks like that. But we still have our 2 pi. Ends up giving us a value for the period, should be just in straight up seconds, of 1.53 seconds. Now if I was going to do a 2 sig fig, that would be 1.5 seconds. Now why am I doing a 2 sig fig? Because we're dividing by a 2 sig fig number there. That's what gives us the 2 sig fig answer. You will see something a lot like this on the test, where you're required to use all of the equations and eventually end up at your answer.